The James Webb Space Telescope, JWST, has revealed an extraordinary phenomenon. Beams of illumination emanating from a distant urban area located light-years away. This revelation has reignited discussions about the possible existence of extraterrestrial civilizations. The telescope focused its observations on the closest known exoplanet to our solar system, Proxima Centauri b, and discovered unusually rapid bursts of light. Could these emissions be evidence of an advanced alien society? Stay tuned for further updates. For years, both public and scientific communities have been captivated by the idea of life beyond Earth. Any indication of extraterrestrial life has been met with great enthusiasm. A significant breakthrough occurred when the JWST provided convincing evidence of the presence of life elsewhere in the universe while examining the vast expanse of space. This powerful instrument uncovered something remarkable on a distant exoplanet, lights resembling those from human-made cities, increasing the likelihood that an alien metropolis exists on that faraway world. This discovery has generated considerable excitement and curiosity within the scientific community, as it could represent the breakthrough they have been waiting for. It suggests the presence of intelligent beings operating civilizations in ways we are just beginning to understand. Being aware of these city-like lights from an astonishing distance of 4 light-years away, NASA engineers are astounded, pondering how long they might have been visible in space, awaiting our technological advancement to detect them. David Kipping, an astronomer at Columbia University, described the planet as particularly complex. Unlike most rocky planets that absorb sunlight and emit energy as infrared radiation, this exoplanet behaves differently due to its unique relationship with its host star, Proxima Centauri. This discovery emphasizes the significance of the JWST. Its capability to capture infrared wavelengths was essential in identifying Proxima Centauri b's peculiar behavior, which is crucial for understanding the planet's atmospheric conditions. Researchers plan to continue utilizing the telescope to study the atmosphere of this planet in greater detail, hoping to determine whether it might be habitable. The JWST is particularly adept at detecting infrared light, enabling it to observe phenomena on Proxima Centauri b, even during the night. Many telescopes struggle to detect faint light in the vastness of space's darkness, but the JWST excels at picking up even the faintest glimmers. This makes it an ideal tool to confirm if the alleged city lights on Proxima Centauri b's dark side are indeed real. The telescope can detect artificial light in the vacuum of space, provided it falls within a very specific frequency range, much narrower than the light emitted by regular stars. Proxima Centauri b exhibits a dynamic interaction with its star, which has a significant impact on its environment. Like many planets that orbit stars, it captures intense energy from Proxima Centauri. As the planet revolves around the star, it undergoes cycles of day and night, much like Earth, experiencing scorching heat during the day and cooler temperatures at night. The range of temperatures on Proxima Centauri b is vast, primarily due to its composition. For example, if the planet has an atmosphere, the difference in temperature between day and night would be extreme hot on one side and frigid on the other. This dramatic thermal fluctuation is a key area of interest for astronomers, as it provides useful information about Proxima Centauri b's atmospheric makeup. The JWST, with its ability to image in the infrared spectrum, can effectively examine the planet's thermal emissions, revealing details about its atmospheric properties. Interestingly, the orbit of the JWST around Earth coincides with Proxima Centauri b's orbital period, enabling scientists to make detailed observations of its daylight cycles every 11.2 Earth days. If Proxima Centauri b possesses an atmosphere, the next step will be to analyze its chemical composition to determine if it could support life. Detecting elements like oxygen, water vapor, and methane would imply that the planet has the potential to harbor life. This would involve studying the light that enters the planet's atmosphere, a complex process. However, While the JWST is great for describing planetary atmospheres, it is primarily designed for other tasks. Its expertise lies in studying the concentrations of water vapor, carbon dioxide, and methane. But it is less adept at detecting free oxygen, a crucial sign of life. Nonetheless, the telescope can search for other key indicators, like ozone, which signals a healthy atmosphere. Scientists are looking into the data gathered from the JWST. The hunt for distant worlds continues. The lookup is bringing us closer to answering the question of whether we are alone in the universe. It's important to note that the JWST can only observe a limited number of the closest exoplanets to Earth. For more detailed studies of planetary atmospheres, astronomers will rely on ground-based observatories like the Extremely Large Telescope, ELT, which is set to begin operations in 2027. The ELT is designed to offer a deeper look at the far-off structures of exoplanet atmospheres, providing greater clarity and specifics regarding their capacity to support life. Scientists are eagerly awaiting the launch of upcoming spacecraft telescopes, like the ELT, in the interim. The JWST continues to be a valuable instrument for looking at distant exoplanets. The JWST has limitations but continues to offer critical information that may alter our perception of what exists beyond our solar system. Researchers have ambitious plans for future space telescopes. They aim to develop technologies that reduce starlight interference, allowing for better observation of the planets around them, similar to using your hand to block the sun to see. More clearly, these upcoming telescopes will be able to focus on the faint light reflected by exoplanets, making it easier to study their environments and assess whether they might be capable of supporting life. However, this task is far from simple. Stars are incredibly bright, often vastly outshining their surrounding planets. This radiance makes it difficult to detect the faint light that planets reflect, which is essential for studying their characteristics. To deal with this challenge, scientists are working on several novel approaches. One of these methods involves the use of coronagraphs, devices placed inside telescopes to block out the star's rays while allowing the planet's light to pass through. By carefully shaping the light waves, coronagraphs can significantly reduce the brightness from the star, making it simpler to recognize the dim light from exoplanets. An additional promising strategy is the massive starshade, a flower-shaped spacecraft flying tens of thousands of kilometers away from the telescope. Before the starlight even enters the telescope, the starshade blocks it, allowing only the light from exoplanets to reach the instruments. This technique could be particularly effective in observing planets in the habitable zone of their stars, where liquid water and possibly life could exist. However, these cutting-edge technologies necessitate extraordinary precision. For instance, the alignment of a starshade must be perfect to fractions of a millimeter over vast distances. Moreover, these innovations must overcome the limitations posed by space missions, including the need for miniaturization, energy efficiency, and the ability to withstand the harsh conditions of space. Despite these obstacles, the potential rewards are enormous. Successfully observing and analyzing the atmospheres of exoplanets could lead to the discovery of biosignatures, chemical indicators of life, such as oxygen, methane, or water vapor in specific ratios. These molecules might point to biological processes that suggest life exists beyond Earth. Researchers are also exploring ways to directly image distant worlds in greater detail. Future telescopes could be equipped with advanced adaptive optics, which adjust for distortions caused by Earth's atmosphere or the movements of the telescope, results in more detailed images. Combined with technologies that block starlight, these improvements could allow scientists not only to detect exoplanets, but also to map their surfaces and study their climates. The development of next-generation space telescopes represents a significant leap forward in our quest to answer one of humanity's most profound questions. Are we alone in the universe? By enhancing our ability to observe these distant planets, we are getting closer to determining whether there is life beyond Earth. potentially transforming our understanding of our place in the cosmos. Space exploration's future and the search for life beyond Earth are advancing at a rate never before seen. As astronomers and scientists delve deeper into the mysteries of distant exoplanets, the James Webb Space Telescope, JWST, is ushering in a new era of cosmic discovery. The data it gathers is helping astronomers make groundbreaking revelations about the structure, composition, and potential habitability of other worlds. With each new piece of information, we edge closer to the ultimate question: is there life beyond our planet? The discovery of Proxima Centauri b is just the beginning of what could become a major turning point in how we approach the study of extraterrestrial life. Proxima Centauri b, being the closest known exoplanet to our solar system, has been a focus of intense research for years. However, until now, finding concrete evidence of life, such as artificial light or signs of civilization, was a dream for many scientists. The fact that such light has been detected by the JWST only enhances the hope that one day we may communicate with other intelligent life in the universe. This kind of discovery fuels both scientific curiosity and public imagination, inspiring new generations to think beyond the confines of Earth. As the JWST continues its observations, it goes beyond just looking for artificial lights, focusing also on planetary atmospheres, their chemical compositions, and how these factors could support life. The search for biosignatures, like methane or carbon dioxide in the right concentrations, is vital for understanding whether these planets have the right conditions for life. The JWST is equipped to examine these atmospheric components in a way no other telescope has been able to, shedding light on the potential of distant worlds where life similar to Earth's could flourish. One of the most fascinating characteristics of Proxima Centauri b is its location within the habitable zone of its star, where conditions might be right for liquid water to exist on its surface. The habitable zone is the region around a star where temperatures are just right, not too hot and not too cold for liquid water to form. This is considered an important aspect in determining whether a planet could harbor life. Water is essential for life as we know it, making knowledge of an exoplanet within a star's habitable zone a key target for future missions. In addition to finding life-supporting planets, future space telescopes will also focus on the complex connection between exoplanets and their stars. Some planets, like Proxima Centauri b, are tidally locked, meaning one side always faces the star while the other remains in darkness. This could create extreme temperature differences between the two sides of the planet, which would affect the planet's climate and its potential to support life. Understanding these conditions is critical for astronomers as they assess the likelihood of habitable environments on exoplanets. The development of technologies for preventing the bright light from stars is another major advancement in space exploration. Without the capacity to isolate starlight, it would be virtually impossible to see the faint light of distant planets. The coronagraph and starshade technologies cited earlier are excellent examples of how scientists are tackling this challenge. By obstructing the overpowering brightness of a host star, these tools allow telescopes to detect the faint light reflected from orbiting planets. This light might contain essential information about a planet's surface conditions, atmospheric composition, and even its capacity to host life. An especially thrilling advancement in this realm is the concept of direct exoplanet imaging through the use of advanced adaptive optics and light-suppressing instruments. Astronomers hope to capture high-resolution photographs of planets as they orbit their parent stars. These pictures could not only reveal further insight into a planet's atmospheric properties and chemical composition, but also display features like bodies of water, land masses, or large-scale weather systems, giving humanity a look like no other at distant worlds. Such capabilities would mark a substantial breakthrough in our exploration of habitable exoplanets and significantly enhance our comprehension of their ability to sustain life. As the global effort to explore the cosmos intensifies, the James Webb Space Telescope JWST, along with upcoming missions, will play a crucial role. The JWST's proficiency in spotting minute energy signatures, dissecting atmospheric components, and evaluating potential biosignatures is changing contemporary astrophysics. As scientific advancements and technological understanding grow, we inch ever closer to information that may completely redefine how we think about life in the universe. The rapid advancement in space exploration and astrobiology is presenting new opportunities previously unimagined. Researchers and astronomers are continuing to dive deeper into the cosmic unknown, the JWST leading the charge into a bold, new era of discovery. The treasure trove of data it provides is already enabling astronomers to draw groundbreaking conclusions about the structure, chemistry, and habitability of remote exoplanets. Each new data point moves us closer to answering one of humanity's greatest questions. Are we alone in the universe? The revelation of Proxima Centauri b's distinctive features may represent only the beginning of a revolutionary change in the way we approach extraterrestrial research. As the closest known stellar neighbor to our solar system, Proxima Centauri b has, for a long time, been the subject of rigorous scientific study. Yet until now, tangible evidence of alien life, such as possible artificial light or indicators of intelligent infrastructure, remained purely speculative.